All right, now problem 3. It says, given that SR to the M is equal to R to the NS, find an expression for N in terms of M. Now, this expression actually was in the dihedral group section, but if you forgot, you could rederive this. So let's draw a picture because that's always a good thing. So I'll draw my hexagon A, B, C, D, E, F. All right, so if I'm starting from scratch and I want to look at this, what I want to do is multiply each rotation on the left and on the right by S. Now what is S? S leaves A fixed, so S is equal to BF CE. Okay, so S switches B and F and C and E. All right, so let's do the rotations. So let's see, let's say R. R is going to be A, B, C, D, E, F. Here, let me move it back a little bit. Let's do this. So I have room. Here's what R is. Okay. Right. And then let's see R squared. Now I mentioned that R squared takes A to C, and it takes C to E, and takes E to A, so that closes off, and then it takes B over to D, and D over to F, and F back to B. So that's R squared. R cubed, well, that takes A over to D, and then it takes B over to E, and it takes C over to F. And then R to the fourth is going to take A all the way around to E, and then it takes B to F, and then it takes C to D. Well, let's see, that doesn't look right. A all around to B, E. Oh, I'm sorry, yeah, I'm sorry. I have to follow it up, right? A around to E, and then E is going to go around to C, so I did this wrong. AEC, and then it's going to be B, and then B goes to F, and F goes to D. Now notice that R to the fourth is R squared inverse, so R to the fifth is going to be equal to R to the fifth is R inverse, and that's equal to A, F, E, D, C, B. All right, so what we want is to compare S multiplied on the left and on the right. So if I do SR, that means do R first and then S. Okay, so if I do R first, I'm going to start with A, and A goes over to B, and then S takes B to F. So that's going to take A to F. Now I really don't have to go any farther because I know this is a flip and not a rotation. So this is the rotation that takes the flip that takes A to F. The flip that takes A to F also takes B to E and C to D. All right, so that's SR. Okay, and then we can look at RS. RS means I do S first and then R. Now, if you look at this, S doesn't take A to anything, and R takes A to B. So RS is going to be AB. It's going to start with AB, but we know that RS is a flip. It's not a rotation, because rotations multiplied by rotations are rotations, but rotations multiplied by flips are flips. So this is a flip that flips A and B. So if that flips A and B, then the next one must be flip C and F. And then the next one must flip D and E. Okay. All right, now I could work my way down the list like this. Let me start at the end and see what happens. So here, if I take SR to the fifth, Well, that means I do r to the fifth first and then do s. So that a is going to go to f. And then what does s take f to? S takes f to b. So it takes a to b. Now, it looks like it's starting out as a rotation, but in fact, we know that sr to the fifth is a flip. It can't be a rotation. So that's a to the b. Now, what flip takes a to b? It's the flip around the midpoint of the segment AB. So it's also going to take C to F and D to E. And you can notice something. SR to the fifth is the same thing as RS. Okay? SR to the fifth is equal to RS. And let's look at, we do r to the fifth s. Well, we've already found that s. We don't, well, all right, yeah, let's look at r to the fifth s. Sorry, where's my mouse? Well, again, we're doing s first, so s doesn't take a to anything. And r to the fifth takes a to f. So this is going to be the flip that takes a to f. Now, in this case, the flip that takes a to f is around this axis, which is the midpoint of AF. So that's going to take B to E and C to D. Let's just write it down here, BE. Well, let's write it over. It's not good to do that. Let me just unzoom a little bit. Okay, so that's A to F, and then I've got, what did I say? I think I said B to E, C to D. And that's equal to SR. All right, so you have SR to the fifth equals RS. And r to the fifth s equals SR. All right, now you could continue this pattern and work the relationships, and you would find that SR squared is equal to r to the fourth s. And you'd find SR to the fourth is equal to RS squared. And you'd also find that SR cubed equals r cubed s. So what's the relation here? Well, notice that in each one of these cases, the exponent on r on the left and the exponent of r on the right adds up to 6. Okay. So you have r to the fifth s equals sr to the first, sr to the squared equals r squared s, and so on. So the relation seems to be, if we have s r to the m equals r to the n s, that implies that m plus n is equal to 6. Now remember, if you have r to the sixth, that's the identity. So this relation kind of makes sense. So in this case, we have m equals 6 minus n, or here I say n equals 6 minus n. Okay, so that's kind of the brute force trial and error method of doing this. Now there's a more elegant method. Okay, we know that SR to the, let's see, how do we write this? SR to the M is a flip. We know that from the chapter. Flip meaning reflection. Okay. So what does that mean? That means, so SR to the M squared is equal to the ID. So that means that SR to the M is equal to SR to the M inverse. It's its own inverse. Now, on the other hand, you may observe that if I take SR to the M and multiply that by R to the something times S, what will I get? Well, if this R to the M and this R power combine together to give me the identity, then when I have less of S as an S and S, which also gives me the identity. So I can write here minus 6 minus m is if I use the associative law, that's the same as r to the 6th s, and that's just going to be equal to ss, which is equal to the identity. Okay. I can do the same thing on the other side if I take r to the 6 minus m s times sr to the m. If I do this, this is equal to the SS's cancel. I can write this as SS times r to the m, and that's equal to r to the 6th, and that's equal to the identity. So what does that mean? That means that r to the 6 minus m s is equal to sr to the m inverse. But sr to the m inverse is just equal to sr to the m. So this fact, that means that this is equal to sr to the m. Okay, so I have r to the 6 minus ms equals sr to the m. So that tells me my relationship. Okay, so r to the ns equals sr to the m if and only if n equals 6 minus m. Same result, but a more elegant way. Okay. So that's the relationship between the two. But again, that formula was explicitly in the chapter. I can pull that in and show you. Let's see if I can get over there. And let's see. Oh, that's right. It's right here. And then that was derived earlier. Okay, so that's how you could get it. All right, now let's look at the next part of question 3, which is find all rotations that commute with S. All right, now I want to use part A. Okay, so part B is find all rotations. So I'm going to use S r to the 6 minus m equals r to the ms to, I think I did that backwards, sr to the m equal r to the 6 minus m s to find all rotations that commute with S. Okay, now you think about this. If I have, so first of all, I have any rotation has the form r to the m for some m. Okay. We have the basic rotation, and we take powers of it, and that will give us any rotation. Okay, so rotation commutes with S. Rotation r to the m commutes with S. That means that r to the ms is equal to sr to the m. But up here we know that sr to the m equals r to the 6 minus ms for all rotations. Okay, this relation is true for all rotations. Okay. So I'm sorry, I messed this up. This should be sr to the m. Trying to write too fast. sr to the m. Okay. But sr to the m, as I said, so what I can do is plug sr to the m, I can plug this in for sr to the m. So if r to the m commutes with S, I must have r to the ms is equal to r to the 6 minus ms. Now, when can that happen? You could say that m is equal to 6 minus m, which gives me m equals 3. Now there's another option also, because r to the 6 is identity. We'd also have, we could have m is equal to 0, because r to the 6 is the identity. Okay, but that's that tells me that that would be the identity. So the two cases, the two rotations that commute with S, we have ID, which we already knew, and r cubed. R cubed also commutes because of this relationship. And you know, you could have, if you did this exhaustive approach, you could have seen that. It would have come out of here. You'd see which one commutes. So if you had done the exhaustive approach, the part A would have given you part B. All right, so that's probably the hardest problem on the first test. It probably would have taken most of your time.